This video is about complex impedance. It corresponds to section 10.2 of the Applied Analog Electronics textbook. Complex impedance is one of the three primary topics of this course. Those three topics were voltage dividers, complex impedance, and negative feedback amplifiers. So complex impedance is a crucial concept. Luckily, it's not a difficult concept. It turns out that complex impedance is basically the same concept as resistance. We had resistance is voltage over current, and what we have is impedance, written with a Z, is also voltage over current. It's the same concept, almost. For resistance, that really only made sense when we were looking at DC voltages and DC currents. Impedance is for AC voltages and currents. And in both these cases, I'm talking about a single component which has got two ports. And we're looking at the voltage across the component and the current through the component. So what difference does it make that we're talking about alternating current rather than direct current? Well, basically, what we need is to look at the voltage and the current as sinusoids. More complicated waveforms basically get handled as sums of possibly infinite numbers of sinusoids for mathematical purposes. But we can do essentially all the analysis we need to do by looking just at sinusoids. And the general sinusoid is something like cosine of omega t plus phi, where that omega is called the angular frequency, and phi is the phase, or if you want to be very pedantic, the phase at time zero, because this whole thing here inside the cosine can be thought of as the instantaneous phase. Okay, so that's our general form of a sinusoid, except I hate trigonometry. And there's no real need to do trigonometry because we can write cosine in terms of exponentials. If we use Euler's formula, this just becomes e to the j times omega t plus phi plus e to the minus j times omega t plus phi divided by 2. And so if we're just adding and subtracting things, we can take a look at what our systems do just with the exponentials and forget about trigonometry. It's just not necessary for us to get into that mess. So what happens if we put a voltage that's, say, some amplitude times e to the j omega t plus phi? What current are we going to get? Well, as long as we're dealing with what are called linear components, and that includes resistors, capacitors, and inductors, and combinations of them, as long as we're dealing with linear components, the current will have the same angular frequency. And so the current I will be some amount b times e to the j omega t plus, and then we're going to have some other phase, say. Okay, so but they'll have, the crucial thing is that they will have the same angular frequency. And that means that if we do a division here, we're going to get z, which is v over I, being a over b times e to the j phi minus c. Notice that there is no dependence on time there. So this is a constant. For any given component, any given linear component, we're going to get a single complex number here that is the impedance of that component. Now, that'll be true for a particular value of omega. At a given frequency, everything here is going to be constant. But if we picked a different frequency, the relationship between V and I may be different because these two formulas, the only thing we were guaranteed was that the omegas would match. If we have a different value of omega, we may have a different value of B and a different value of C. Things can change. So that this constant with respect to time, but it may end up being a function of omega. And in fact, that's what we're going to do a lot of the time, is to be plotting what is the impedance as a function of frequency. How does it change with frequency? Because that's going to tell us a lot about what our devices are doing. And there's a fancy name for representing this complex number. This is sometimes referred to as a phasor, because it's telling you what's happening to the amplitude, and it's telling you what's happening to the phase. And it doesn't really matter whether you remember the term phasor or not. It's just kind of a cool word. We can look at what happens to impedances in series or impedances in parallel, because we're often going to be hooking up our components in series or parallel, and it'd be nice to know what happens with them. So if we have two impedances in series, let's say this is Z1 and Z2. Well, what happens for the voltages? Well, the voltage across here is V1, the voltage across here is V2, the voltage across the entire stack is V1 plus V2. The current through here is I. The current through here is also I. It doesn't have anywhere else to go. So we end up with that the impedance across the whole thing is going to be V1 plus V2 over I, which is just Z1 plus Z2. It's exactly the same reasoning we did for resistors and resistance, because voltages add, current stays the same, so impedances or resistances add. And similarly, if we've got a bunch of impedances in parallel, Z1, Z2, Z3, we're going to have the same voltage across all of them. We will have currents I1, I2, I3. Currents will add, and so we will have the impedances whole thing is V divided by I1 plus I2 plus I3. And if you do a little bit of algebra on that, you get the same thing as we got for resistances. This is going to be 1 over Z1 plus 1 over Z2 plus 1 over Z3. So impedances behave exactly like resistances because they have the same underlying fundamental concept of being voltage divided by current. Okay, so what else do we want to do with complex impedance? Well, for general impedances, that's probably all we need to have, and we'll look specifically at impedances of capacitors in a separate video.